In the previous video, we introduced the exponential function as being the inverse of the natural log and discussed some of its basic properties. What we would like to do now, of course, since this is a calculus course, is talk about differentiating and eventually anti-differentiating the exponential function. Now, in order to do so, when we write down y equals e to the x, since we don't know yet the derivative of e to the x, we don't really have a good approach to calculating that derivative in its current form. You could, of course, try to write out the limit of the difference quotient and use a definition, but that doesn't seem to be the most pleasant approach, so instead we're going to use logarithmic differentiation because we know the inverse of the exponential is the natural log, and we know what its derivative is. So let's go ahead and do that. So for logarithmic differentiation, we take the natural log of both sides, and when you take the natural log of e to the x, you're simply left with x, because one of our properties told us the ln and the e cancel. So we now differentiate both sides with respect to x, and recall the derivative on the left is an implicit derivative. So you differentiate that natural log exactly how you would like to, and then multiply by its derivative, y prime. And on the right, the derivative of x with respect to x is just 1. So y prime is equal to y. And if we look above, we see that y, the function we started with, is really just e to the x. So y prime is also e to the x. So to summarize, using properties of the inverse of the exponential, that is, properties of the natural log and implicit differentiation, we have found that the exponential function e to the x, and it turns out it's the only such function in calculus, is its own derivative. Now, the most common application of this, or how we encounter it frequently, would be using the chain rule, where we have the derivative of something like e raised to a function u. The chain rule tells us we take the derivative of the outside function. Derivative of e to the x is e to the x. You evaluate at the inside function, u of x, and then you multiply by the derivative. So this comes from just using the chain rule. Let's look at a few very common examples. So let's start off with the function y equals e to the x squared natural log x. So let's just go ahead and differentiate this directly using the chain rule. So dy dx is going to be the derivative of the outside function, so e, evaluated at the inside function, x squared ln of x, multiplied by the derivative of that inside function. So this will equal e to the x squared ln x. That kind of comes down for the ride. And then to differentiate x squared ln x, we use the product rule. We have one function x squared times a second function natural log x. So we take the derivative for the first times the second plus the first times the derivative of the second. So that would be e to the x squared ln of x multiplied by 2x ln x plus x. So let's look at a second example. So we have y equals x divided by e to the square root of x. So because of the form of this function, x over another function, we can differentiate this with the quotient rule. So the quotient rule tells us, and we'll kind of talk our way through this, should be low d high, and the derivative of x is 1, minus high times the derivative of that function in the bottom. So we're multiplying by the derivative of e raised to the square root of x. So by the chain rule, derivative of the outside, evaluated at the inside, times the derivative of that inside function, all divided by the bottom squared. And in this example, I see one very basic simplification. Note, each of the terms contains an e to the root x. So what we could do is cancel it off, one of them from each term. what that will leave us with is 1 minus x over 2 square roots of x, which would really just be 1/2 square root x, all divided by a single e to the square root of x. One last differentiation example, and hopefully this is starting to feel familiar. So using the chain rule for each of these terms. So for e to the 2x, when we differentiate, you say derivative of the outside, evaluated at the inside, times the derivative of the inside. So note, in general, if you want to differentiate e raised to a constant x, this is always going to be by the chain rule, ke to the kx. Now plus, for this second part, e to the minus 1 over x squared. Same idea. We say take the derivative of the outside, evaluate at the inside, and then multiply by the derivative of the inside. So let's just note, minus 1 over x squared is equal to minus x to the minus 2. So when you differentiate that inside function, the minus 2 comes down, so minus a minus 2 is a positive 2, and the new power of x is minus 3.